Hello everyone. So today we come back to continue the class on Monday. Okay. So today the answer that I want you to understand, okay, the thing that I want you to understand is two things. One is that how can we give the symbol to the microstates? So this one we're gonna talk about the term symbol. Okay, so these are the symbol to the ground to the microstate. Okay, and the second question is that what are the most stable microstates? Okay, so this one we're gonna call it ground state. Okay, so there are two things that you have to be able to answer and submit the homework at the end of this lecture. You can start working on the homework, and then on Monday is the due date. Okay, Monday after class. Okay. So if you don't remember what is the microstate, what are the microstates? Okay, so these are the microstate. The possibility of the electron configuration, electron arrangement. Okay, so for example, in this case is P2. So P2 mean you have two electron in the p orbital, and the p orbital the p orbital they are 3 ml value. So actually they have 6 box that electron can put in. Okay, and P2, the possibility of the P2 configuration we can calculate that it is 15 possible electronic arrangement. All of these are the microstates. Okay, so you know the P2 configuration gonna give you 15 microstates. Okay, and the calculation for the microstate we done it already. So after we get the microstate, we're not gonna write it down to communicate. We're gonna find a symbol for them. Okay, so the symbol for the microstate are called term symbol. The term symbol are composed of these 3 letter or 3 number. So we're gonna have L and 2s plus 1. This one we call it spin multiplicity, and J is the spin orbit coupling. Okay, so the L is the orbital angular momentum. Okay, so you can think of L is actually come from the ML. You have many ML in the system. Every electron have their own ML quantum number, and this spin multiplicity come from the MS or the spin quantum number of the electron. So in the system, you have many electrons. ML gonna coupling together. If you have like 2 electrons, these 2 electrons gonna coupling together and give a combination that can result to L, the capital M, capital L here. And for the MS as well, the electron can coupling together to give the combined MS, but the combination gonna have their system, okay, which we will talk about it later. We call this one as the Russell-Saunders coupling, okay. And the last one is the one that result from spin and orbit, okay. So it comes from the ML and MS coupling together. As you maybe I haven't show you clearly that MS are vector and ML also a vector because they have the direction and also they have the magnitude, right? So when we combine these, it's combined like a vector. Okay, so L is the total orbital angular momentum. So it means you combine the ML together, and S is the total spin quantum number, or you can think as you combine MS together. Okay, so let's see how we do that. Okay, so the Russell-Saunders is actually the one that focus on the many electrons, many electron system, okay, in an atom. Okay, and they care that they predict that interaction are the coupling that I'm talking about, like spin and spin, orbit and orbit, and orbit and spin. So these are the three possible coupling, but the most important one, that the strongest coupling is spin-spin coupling, okay? And the second one is the orbit-orbit coupling, and the spin-orbit is the least one, okay? So when we do this, that means we're gonna care most about the spin-spin and orbit-orbit. This one we're gonna give it as the last priority, okay? So sometimes it can be ignored. The J value, sometimes we can ignore this value because it's just so small. The interaction is so small and it doesn't affect in energy that much. Okay. So first we find these two first, spin coupling and orbit coupling. So how can we find the spin coupling and orbit coupling? Look at the symbol first. So when you have this, for example, this microstate. So as you know that ML value, we have +1, -1, and 0, right? So these are the ML value. And for the MS value, this one are +1, +half and +half, right? So in this case, I assign that spin up is +half, spin down is -half. Okay. So these are the value of the ML and MS. So you can look. Last time I have the exercise or in the Kahoot, I asked you to find the ML and MS of every electron. Now you can find the ML and MS. So for example, in this case, if I ask what is this one, so you can say that it's ML of +1 and spin of +1. So the symbol for this microstate, I can say that is 1 plus and -1 plus. So plus is the spin, and the 1 and -1 is the ML. Okay, so in the microstate like this, 1 plus 0 minus is mean 1 electron gonna be ML of +1 with spin of +half. So 1 plus mean this, and 0 minus is the second electron is 0 ML and -half. Okay, so this is the symbol of the microstates. Okay, so after we when you saw the symbol, or when you look at the table, when you look at your distribution, you can find the ML and MS of every atom. Okay, of every electron. So this is the microstate, one of the microstate that is possible in the 15 possibility of P2, right? P2 arrangement. So ML come from the letter ML here, the total, opposite. ML is the total orbital, and MS is total spin. Okay, so ML come from the combine of ML, of small ML. MS is the combination of the MS, of the small MS, of combine of electron in the system. And the ML value will give you the L quantum number that we're going to use here. We want to find the L here, right? So the ML has the value from +L to -L, okay? So total you have 2L + 1 value. For example, if you want to get, if you say that your system have L equal to 1, it means you must have the ML value of +1, 0, and -1. Okay. Or if you say that your L value is 0, it means you must have the system with ML of just 0. Okay. So this is the L. L comes from the range of the ML. And the capital ML come from the sigma ML, small ml. Okay, so you see that you found 15 possibility, and you find the ML/MS of the system, and then you find the sigma ML, and then from the sigma ML you can get the L value that you can use to write the term symbol. Okay, so don't worry about it yet. We can do it easier way. Okay, so MS is the same, quite similar definition. So MS has the value from plus S to minus S. Doesn't have to be passing zero, because S can be an not an integer. Okay, so for example, if you have S value of equal to 1, it means your MS have to be 3 value, which are -1, 0, and 1. Okay, but your system can have the S of half. Okay, so if you have capital S of half, it means your MS have to range from half and minus half. Or if you have S equal to 3/2, so the MS have to range from 3/2, 1/2, minus half, and minus 3/2. Okay, so this is the how to get the S and L. Okay, how to get L, how to get S. Okay, but this one, don't forget that after you got S, don't be so happy. Okay, don't forget that you have to calculate a little bit more to S plus 1 to get the spin multiplicity. Okay, to put in the symbol. Okay, so this is the idea. First, you found the L and S value. Okay, and then later we can find the J later. Okay, so to do this, the simple way is to build a table. Okay, after you distribute them into 15 possible electronic arrangement, okay, you can reduce this one. You have 15 possible microstate, right? This is 1, 2, 3, 4, 5, 6. So you have 15 microstate. Each microstate, you can find the ML and MS of them. For example, if I say that Px is plus 1, Py is minus 1, and Pz is 0, you can assign it differently. Okay, so you can assign differently, but please assign it. Okay, so for example, if I pick this one, so this value is going to be minus 1 plus and minus 1. Sorry, minus 1 plus and minus 1 minus, right? So you can find that combined ML gonna be equal to minus 2 ML of this system, and MS of this system is, of this microstate, is 0. So ML of minus 2 and MS of 0, so it means this one, right? This is this microstate. Okay, let's try another example. So for example, this one, it would be plus 1 plus, right? Spin up, and minus 1 spin down. So the combined ML going to be equal to 0, and MS going to be equal to 0. So 0 and 0 is going to fall into this one of these. So it is actually this microstate, right? This is the microstate that I'm talking about. Okay, so from these 15, you can put in the table. Okay, you can put them into the table. And now we don't care it anymore. Whether what is it come from what microstate. We just gonna count. What we care right now is we gonna count how many microstate that fall into each table. So we can reduce this one to just X because we just want to count how many microstate on each box. Okay, so you can see that right now you have in the middle 0, 0, you have 3X. You have 3 microstate that fall into this box. You have 2 microstate that fall into this box, okay? And you have 1 microstate that fall into these 2 box, okay? So then we, since we don't care about the term symbol, the symbol of the microstate anymore, we're gonna collapse them into this image, right? This we just count how many microstate in each box. Okay, so this is what we're gonna do later. Okay. Okay, and what I have talked about so far is that we want to find the L and the S of the system, right? Okay, so what is L? L is the combine of the ML, right? Okay, and similar to ML, we want to replace them with the letter, with the alphabet. Okay, so if you got L equal to 0, this one gonna be capital S. If you got L of 1, we're gonna have the symbol of P. Okay, if we have L of 2, it's gonna be symbol of capital D. So now we change to capital letter. Earlier, when you do the atomic symbol, we use the the lowercase letter, right? Lowercase alphabet for represent the orbital of single electron. But now it's the combined electron, so we're gonna use the capital letter. Okay, so this is L. And then what is it? Combine. So I just mentioned that the combination come from the vector combination. Okay, so you can see that because of the direction like this, we can get different combination. Like if you have the value of L of the same value, they can result in totally cancel each other out, or if the angle is like this, that can result in the number of 1. Okay, or if they combine like this, they can get the level of 2. So this page just to show you that why 1 and 1 can result into many value. So because it's combined by the vector. Okay, so it can get the L equal to, which is the D state, or L equal to 0, which is the S state, and L equal to 1, which is the P state. Okay, so same thing with P3 system, you can get a range of different state. Okay, so this one you don't have to care much, just the image why they result in many value, because they combine by the vector. Okay, and for the spin come from the combine of the MS, so result in the total spin quantum number S. Okay, and because this one the angle doesn't affect much, so they have only spin up and spin down, right? So these are the combination of the spin that can result in S, in the capital S. So okay, just show you that it comes from the combine of the vector. And the spin multiplicity, after you got the S value, we're not going to put the S value on top of the term symbol yet. We're going to calculate a little bit more to get the spin multiplicity. So if you got S equal to 0, spin multiplicity going to be equal to 1. And we're going to call this term as singlet. It's going to be singlet state. If you got S equal to 1, for example, 2S plus 1 going to equal to 3. And this one we're going to call it triplet state. Okay. So these are the term, the one that we're going to put on the term symbol. Okay, so let's do it. Okay. So now you got the table of the 15 microstate that you distribute. You can put into this table, okay, based on the ML and MS. Okay, so the way to do that is you draw the biggest box, biggest rectangular or square box. Okay, out the biggest one first. Okay, out of this table. So you can see that the distribute of the 15 gonna result you the largest box that you can bring out is this red box here. We can take this red box and put the the red box here. We can put it here. We can take it out. And now you can see that the system gonna have the ML ranging from -1 to +1. So this one, we know that this 9 microstate, they are in the same term of L equal to 1. And MS ranging from -1 to +1. So S gonna equal to 1. So the term symbol of this gonna be L equal to 1 is P term. Okay, L equal to 1 is P. So we put the capital letter P here. And S equal to 1, so 2S plus 1 is 3. So it's the triple P state. Okay, so this is 9 microstate combined together to get the triple P state. Okay, so if I ask you backward, triple P, so how many microstate that they represent by the triple P state? So it's 9 microstate. Okay, so you after you use it, you just delete it out. Okay, so find the next largest box. So the next largest box that you can draw out is this one. It's 5 rows times 1 column. Okay, so this 5 microstates gonna be the one that ranging from ML ranging from +2 to -2. So L gonna be equal to 2 and S equal to 0. So this one gonna be the term symbol for this one gonna be singlet D. Okay, L equal to 2 is D and S equal to 0 is singlet. Okay, so you take 5 out. Take 5 microstate out. So this is 9 and 5. So now you have only 1 box left. Oh, sorry, 1 microstate left, and they stay in the middle. So this one gonna be the L equal to 0 and S equal to 0 because they are only 0 value. So it's gonna be singlet S term. Okay, so this represents just 1 microstate. So combine it back. You're gonna know that it's 5 plus 9 plus 1 is have to be equal to your calculation of 15 microstate for P2 configuration. Okay. So these are the way to find the term symbol. Okay. So begin with calculate how many possibilities that you can have, and then you put in the table. Okay, put in the table, and then you try to bring out the largest rectangle out of the table one by one until you get the last one out. Okay, and then you can get the total microstate of this system. Okay, so for example, if we just do focus into just a few boxes, for example, you got 0 plus 0 minus, you can think of the box look like this in the s orbital, right? 0 plus 0 minus. So this one, they have ml of 0, ms of 0. So this one gonna reduce to, so their L gonna be equal to 0 and their S gonna be equal to 0. So it's gonna be singlet S. Okay. Or the system that have distribution like this. So you have 6 microstate together. The ML ranging from, this one have to come out from the big box, okay? You find the big table first, and then you take the small, you take the largest rectangle out one by one. So if you take out and it look like this, L ranging from +1 to -1, so L equal to 1, okay? And MS, S, since MS ranging from -half and +half, so S is going to be equal to half. Okay, so this term going to reduce to P, and 2S plus 1 going to be equal to 2. So it's going to be the doublet P. Okay. Okay. So if I ask you back, so this 6 microstate can be reduced to this term. Okay, you can do backward. For example, if you do the doublet S, you know that ML S is mean L equal to 0. So it means you have only one ML of equal to 0. ML equal to 0. And S of multiplicity of 2. So it means S equal to half. So half is mean that MS come from the +half and -half. So it means actually this one come from the box that look like this, right? MS and ML. So it means they represent 2 microstate. Okay. Or another example, quartet D. So D term is mean L equal to 2. L equal to 2. So ML gonna be the value of 2, 1, 0, -1, -2, right? ML this value, and MS of this value of quartet. So it means that S value is 3 over 2. So the MS value of that will result in S of 3 over 2 is mean MS value of 3 over 2, 1 over 2 minus 1 over 2 minus 3 over 2. Okay, so actually it comes from the table of 5 row. So ML of 5 value and MS of 4 value. So actually it's 5 times 4. So it represents 20 microstate. Okay, so the bigger the term or the bigger the multiplicity, it means it represent more and more terms, represent more and more microstate in that. Okay. Okay, so move on. And then if you recall last time, when I asked you this question, P1 and P4 gonna result in the same number, right? Because, sorry, P4 and P2 gonna give you the same value of 15 microstate. P1 gonna be the same value of P5. If you represent into this this formula, you're gonna get 6 microstate. Because this one, they are what we call the whole formulation. They are the same, I mean, they have, this is 1 electron and 5 hole. But for this P5, I mean, they have 5 electron and 1 hole. So hole and electron is actually the same spin, right? The same ML, but it's just opposite. Okay, so the formulation gonna give you the same answer. If you have the same hole or have the same spin, if you have the same hole or the same electron, you're gonna give the same answer. For example, P1 and P5. So P1 look like this. P5 is actually look like this. And if you draw the hole is the complement to the electron, right? So the hole look like this. The red is the hole. So either you have 1 electron or you have 1 hole. The answer is the same. Okay, the same term symbol that you're gonna resolve. P2 and P4 gonna give you the same answer. Distribute as we saw in the example. Okay, so L and S is the same, but the J gonna be opposite. We're gonna talk about it later. Okay. Okay, so this is what we call whole formulation. So when you got many number like this, D9, don't do the 9 electron, try to calculate from 9 electron. Please calculate by using D1. Okay, so that you can deal with less electron when you combine, when you sum it up, it's gonna take shorter time. Okay, and you know that it's complement to each other. Okay, and so if you can remember, this is going to be in the exam, this is going to be the answer for sure. So I cannot ask something more than this. I'm not going to ask to like F orbital. Okay, and yeah, I can ask you S orbital as well. Okay, so this is going to be one of the question that I can ask. So if you think it, you can remember it, but I'm not going to ask for the answer. I'm looking for the way to derive and to get this answer. Okay. Okay. So again, so we have the whole formulation. So you're gonna know that D6 gonna be same as D4. Okay, so we now know how to get L and S. Now the next step is to get the J. The J value is the spin orbit coupling. J come from L plus S. The value of J gonna come from, the value of J gonna ranging from L plus S to absolute L minus S. So it means if you have okay, if you get this, if you're looking at this one, the J value for this gonna be L plus S, which is gonna be half, and absolute L minus S is gonna be half. So you're gonna have only one J value. Okay, but if you are in this term, so L plus S for the P3, for the triplet P, the J value gonna be ranging from 1 plus 1, which is 2, and then absolute L minus S equal to 0. So you're gonna ranging from 2, 1, and 0. So when you write down the complete term symbol of this one gonna be triplet P. It can be 2, triplet P1 and triplet P2. P0, or you can combine it together to be triplet P210. Okay. But there's going to be one of these that is more stable than the rest. So that's what we call the ground state. And you have to identify the ground state now. Okay. For this one, the value, the term symbol, the complete term symbol for this one going to be doublet S half, right? And that's only one value. So this is going to be the minimum. I mean, if this one are ground state, you can just answer this. Okay. Okay, so the J value, there's no minus value. Okay, it have to stop at 0 or before 0, depend on what are the absolute L minus S that you get. Okay, so this one, J come from the vector combination of L and S as well. So don't have to draw this. Okay, so now we're gonna go through what we call the ground state. Okay, ground state term is the term of the lowest energy. So after you found all the term symbol, we want to know what is the lowest energy. So to get the lowest energy, why do we care about this? Because we want to know what are the state of electron when they are not excited, when they're not involved in any energy, what are the most stable form of them. So we want to get this symbol, why many people care about it. But it's not all the time. Sometimes you want to know how does it got excited, and if they got excited, how did they relax and release energy? What are the state that they got excited? Now it's not ground state. But many of times we're going to care about the ground state, which is the lowest energy state. So the way to do this, we're going to use Hund's rule. You heard about this one when you do electron configuration, right? So Hund's rule, there are 3 rules in the Hund's rule. First one, as you remember, we care about spin-spin coupling. So the one with highest spin multiplicity or the highest spin-spin coupling constant, spin-spin coupling, highest value, you're gonna get it to be the ground state. Okay, so if your system have many state, for example, D2, you got this one. So you know for sure that the answer can be one of these. By Hund's rule, they care about spin multiplicity. So either triple P or triple F gonna be the ground state, not the singlet term. Okay. And if they have if 2 terms, just like in that case, that have same spin multiplicity, which one gonna be the lowest in energy? Is the one that have highest value of L. Okay, highest value of L. So you can see here, F and P. PL is equal to 1, FL equal to SP. F equal to 3, right? So the ground state going to be triplet F, okay? Based on the second rule of Hund's rule. Okay, so for P2, we got, when we do the find all the term symbol, we got singlet D, triplet P, and singlet S. So by Hund's rule, you know that this one going to be the lowest energy, triplet P going to be the ground state. Okay, how about D2? Or D2 I just answer is triplet F, right? Okay. So these are the ground state. Now the last rule is that for J, if you consider the J one, what is the lowest J? You have to know first whether the configuration comes from the half field, less than half field, or more than half field. So what is half field? So for example, p orbital, half field of p orbital is mean 3, right? That they can put in 6, so half of 6 is 3. So whether the electron have more than 3 or less than 3. So for example, P2. For the P2, if you got the P2, they have less than half fill. So if they are less than half fill, the state that having the lowest J value gonna be the lowest energy. The ground state gonna be the one that have lowest J. But if you have more than, if you are more than half fill, if you are more than half fill, for example, you are P4. If you are P4, you have to pick the one that have highest J. So now the whole formulation gonna be different in only in this final step. If you consider J, now P2 and P4 give the same answer so far, right? Except when you consider J, P4 and P2, they give the same answer that ground state gonna be triplet P. But if you consider J, for P2, triplet P, you have the value of L equal to 1, S equal to 1. So you have L plus S until absolute L minus S, which is 0. So you have 3 choices. So for P2, the ground state gonna be this one for P2, for P2 configuration. But for P4, you have to pick this one because it is more than half fill. Okay. So that's all the Hund's rule to find the ground state. There are 3 rules. First consider the spin multiplicity first. If you found only one answer, you can answer it right away. But if you have the same value, like triplet P and triplet F, you can you have to consider the second one. Which one have more speed, have more L value, okay, and pick the one that have more L value. Okay, so the reason for Hund's rule, why is that? Okay, for Hund's rule number 1 is that you have 2 electrons, right? The one that have spin multiplicity of higher energy. Okay, sorry, the one that have spin with higher number gonna be the one in lower in energy, because the one that have spin combined together have spin of low value, is have a chance that they're gonna stay in the same orbital. So you can think of this one. If you combine, so the one that has the combine of spin combine in lower energies mean they have spin opposite spin stay together. Okay, so this is the reason why 2 electrons stay too close to each other, so it's going to be higher in energy. But if you allow the spin to be the maximum, like this, it means electrons going to be for sure far away from each other as much as they can. Okay, so the spin multiplicity going to be higher in this system, and it will result in in lower energy because electrons don't get close to each other. So consider electron as the minus charge. They don't want to stay together. If you force them to stay together, like in this case, stay in the same orbital, they're gonna be not stable. Okay. So this is the reason for Hund's rule number 1. For Hund's rule number 2, why we have to pick the high L. The high L and the low L. The system is that the high L is that the L tell you the direction, right, of the orbital. So the high L is mean they combine in that the electron are run parallel to each other. Okay, so you can see the orbital are pointing in the same direction, and if electron pointing in the same direction, the chance of them to see each other gonna be quite low. But if you have low R value, it means there's some orbital that arrange themselves in opposite direction. So electron with opposite direction gonna have chance to see each other more often, right? So you can think of if two cars run into the same direction and two cars run in opposite direction, the one that run in opposite direction gonna have more chance to meet each other, right? So this one, they don't want electron to meet each other. So this one gonna result in high E, high energy. But the one that run parallel to each other, they're gonna result in lower E. So the ground state is the one that have highest L value because it's gonna be lower chance of electron to meet each other. Okay, so these are the Hund's rule number 1 and number 2. For Hund's rule number 3, it's come from the mathematical calculation. Okay, there's some changing from the plus minus sign when you change from hole to electron. Okay, so there's no description for this, just by mathematics. Okay. And how does it split? Okay, so why sometimes we don't care about J value? Because the spin orbit coupling or J value result in very small in energy difference. So these are the electron in different state. So P, triplet P, singlet D, how much different they are? They are different in this kind of wave number. Okay, so it's quite far apart from the when you consider about multiplicity and L value, they are quite different. They are clear different. But when you split by the J, you can see that they are not much different among them. So sometimes it's not significant enough to care unless you want to get the detailed calculation. You can see these values are close to each other to close to 0, right? Okay, so sometimes the J coupling are not much considered. Okay, so these are the way to calculate the ground term. Okay, so you can see the ground term. In this case, the ground term is the lowest in energy, triplet P. Okay. Okay, so if we care about only the ground term, we can find the shortcut. If I ask you only the ground state term, okay. So far we talk about the full system. You start from the calculate of how many possibility that you can get, and then you reduce them into the term symbol, every term symbol that you have, and use the Hund's rule to tell what is the ground state. Okay. So if I ask you directly, what is the ground state of the system? You can do the shortcut by doing this. So to do that, for example, if I want to find the D3, for example, I sketch the energy level. I know that D orbital gonna split into, gonna have 5 orbital. And I'll arrange, second one, arrange to lowest energy. D3, we're gonna arrange like this, spin pointing in the same direction and don't stay in the same orbital. Okay, so I got number 2 already. Now, number 3, find the spin multiplicity. So combine MS of the system going to be 3/2, right? So spin multiplicity. So this one going to be the S of the ground. S of the ground equal 3/2. So spin multiplicity equal to 4, right? 3/2 times 2 plus 1 equal to 4. And then Number 4, determine the maximum value of ML. Okay, maximum value of ML for this arrangement. How can I get the maximum value? I know that ML can range from 2, 1, 0, minus 1, minus 2. If I want to get the highest number, it means I have to put 2 here, 1 and 0. These three have to stay on these three value, not staying into the minus 2, minus 1, right? I don't want the low number, so I don't put them into this number. I put these three onto 2, 1 and 0. So the ML, the maximum ML that I can get is 3. Okay, so from this you can take this one as the L of the ground term. Okay, so the answer for this one is SPDF. So F term is a quartet F term. So D3 is going to be the quartet F, which is going to be the ground state of this system. Okay, so simple, right? If I ask you only the ground one, you can take the MS of the highest arrangement at the S of the ground term and ML of the lowest energy arrangement as the L of the ground term, and you can get the ground term right away. Okay, so you can practice on using this. Okay, and then where are we go? So I think this one is the two answer, two questions that I want you to answer from this lecture. At the beginning, I mentioned that I want you to find the way to give the symbol and find the ground state of this microstate. So I hope you can do that. And it's going to be the homework. So in the homework, you're going to get different set of questions. So do it correctly. You're not going to do every question, every page. Just look at your assignment, what question set that you get, and do only that. Okay. So before I ending this lecture, I would like to say that, so where are we going to find this symbol? What are the applications that we are going to see this? This one going to be about the one that you talk about when you excite the atom. So there are some experiment or some machine that involved with this exciting of the atom. For example, X-ray photoelectron spectroscopy, or sometimes like using ICP. Okay, so the one that involved with exciting atom, you're gonna involve with getting the ground state and getting excited and relaxed to ground state. So what wavelength that you're gonna get for the ionization or relaxation energy? So this one you're gonna find this one again when you talk about this machine. Okay, and atom excitation are involved with physical phenomena, with natural phenomena like the burning of the color of the flame, why different atoms give different color, why they emit out different wavelength, because their excited state are different. So the energy difference between ground state and excited state, this one comes from the relaxation of the excited state to the ground state, right? When they coming out, giving out the light. Okay. So because of each atom have different term symbol, different arrangement, that's why they give out different color. And this one they can use it to design like the firework, why they have to put some element into there. Okay, so these are involved with the with some phenomena that we can find in daily life. Okay, so don't forget to start looking at the homework. And if you have a question, we can meet again on Monday. Okay, thank you, everyone.